Dr. S. SRINIVASAN, Associate Professor, Chemistry Wing of DDE. Now, we are going to see ancillary chemistry subject. In ancillary chemistry, Unit 5, the chapter is Chemical Kinetics. So, in chemical kinetics, we are going to consider many reactions. So, initially we are going to consider that introductions. Chemical kinetics tells us the speed at which chemical species transform into new substances by breaking and reforming their molecular bonds. In other words, it studies the rates and the process of chemical reactions. So, objective of this chemical kinetic system to learn and differentiate rate of the reaction, order and effect of temperature and the reaction rates. The order of reaction, activation energy and Arrhenius rate equation will be explained and learned to understand the catalysis, its classification and its significance. Content. Chemical kinetics and photochemistry we are going to see. First we are going to consider that chemical kinetics. The rate of the reaction, differential rate expressions, order and molecularity, integrated rate expression for first order, second order and zero order reactions, half-life period, effect of temperature and the reaction rate, activation energy, Arrhenius equation, catalysis, homogeneous and heterogeneous catalysis. First, rate of the chemical reaction. When we talk about chemical reaction, the rate of reaction or reaction rate is the speed at which reactant are converted into product. The rate of speed of reaction can be defined as the change in the concentration of any one of the reactant or product by unit time. It is given by the formula rate is equal to minus dCr by dt is equal to dCp by dt, where dCr is concentration of reactant and at time of dt and dCp is concentration of product at time dt. So, C is indicating concentration. The reaction rates are usually expressed as the concentration of reactant consumed or concentration of product formed per unit time. The rate of reaction generally has the units as a moles per liter per seconds. The reactant concentration, the physical state of the reactant, surface area, temperature and the presence of catalyst are four main factors that affect the reaction rate. The rate of reaction is a powerful diagnostic tool by finding out how fast product are made and what causes the reactions to slow down. We can develop methods to improve production. This information is essential for the large scale manufacture of many chemicals including fertilizers, drugs and household cleaning items. Differential rate equation. Differential rate law are used to express the rate of reaction in terms of change in concentration of a reactant over a small interval of time, that is dt. Therefore, differential form of the rate expression provided in the previous subscription is given by minus dr by dt is equal to k concentration of A and Ax by. The differential rate equation can be used to calculate the instantaneous rate of a reaction, which is a reaction rate under very small time interval. It can be noted that the ordinary rate law is differential rate equation, since it offers insight into the instantaneous rate of the reaction. Rate constant. Rearranging the rate equation, the value of the rate constant k or velocity of constant is given by k is equal to rate bar a to concentration of a to the power x, concentration of b to the power y. Therefore, the units of k, assuming that concentration is represented in moles per liter, are mole and time is represented in seconds. can be calculated via the following equation. K is equal to m s to the power minus 1 m to the power minus n is equal to m to the power n minus 1 and second inverse. The rate constant is defined as the rate of the reaction when the concentration of each reactant is unity. Order of reaction. In chemical kinetics, the reactions are generally classified in terms of order. The order of reaction may be defined as the sum of powers to which the concentration or pressure terms are raised into rate law expression. The first order rate is equal to R is equal to K1 concentration of A. For second order rate R K2 C to the power 2 A or R is equal to K2 Ca Cb. The order of reaction refers to the relationship between the rate of the chemical reaction and the concentration of the species taking part in it. Molecularity. The molecularity of the reaction is defined as the number of reacting molecules which collide simultaneously to bring about the chemical reaction. In other words, the molecularity of an elementary reaction is defined as the number of reactant molecules taking part in the reaction. In general, the molecularity of simple reaction is equal to the sum of the number of molecules of reactants involved in the balanced stoichiometric equations. Example, phosphorus pentachloride gives, decomposition of phosphorus pentachloride gives PCl3 plus Cl2. This is one kind of unimolecular reaction. Similarly, we may consider formation of sulfur trioxide. 2 moles of sulfur dioxide with oxygen gives rise to 2 moles of sulfur trioxide. This is one kind of trimolecular reaction. So, next one, formation of nitrogen dioxide. So, 1 mole of NO reacting with O3 gives rise to NO2 plus O2. This is one kind of bimolecular reaction. Here we are considering NO 1 mole, O3 1 mole. So, middle one, trimolecular reaction, there we have considered 2 moles of sulfur dioxide and 1 mole of oxygen. So, initial one we have considered only 1 mole of PCl5. So, totally first one is 1 mole, in the case of second reaction is having 2 moles, 3 moles, and then third reaction is having 2 moles. So, respectively we may consider that factor as such. It is noted that the molecularity of the reaction is always in the whole number. It is never fractional and it is the theoretical concept. Molecularity cannot be greater than 3 because more than 3 molecules may not mutually collide with each other. Integrated rate equations. The concentration of reactants in the chemical reaction as a function of time. Therefore, such rate equations can be employed to check how long it would take for given percentage of the reactant to be consumed in the chemical reaction. So, it is important to note that reactions of different order have different integrated rate equation. Integrated rate equation for zero order reaction is given by R K is equal to R0 minus R by T, where R0 is initial concentration of reactant when T is equal to 0. So, in the concentration of reactant at time T, so K rate constant. Integrated rate equation for first order reactions. The integrated rate law for first order reaction is Kt is equal to 2.303 log R0 by R, or otherwise K is equal to 2.303 by T log R0 by R. It means that what? This is one kind of a big derivation. So, what I have given in this equation based on the derivation. So, integrated rate equation for second order reactions. For second order reaction, the integrated rate equation may be written as Kt is equal to 1 by R minus 1 by R0. Half life period. The half life of a chemical reaction can be defined as the time taken for the concentration of a given reactant to reach 50% of its initial concentration, that is time taken for the reactant concentration to reach half of its initial value. So, whatever it is, what we have taken that initial stage, that it may be reduced into half of the portion. So, it is represented by the symbol T of. It can be related to the corresponding rate constant. The half life of first order reaction is constant, that is related to the rate constant for the reaction T of is equal to 0.693 by K. For first order reaction, the half life is independent of concentration and constant over time. Since the reaction order is second, the formula for T of is equal to K to the power minus 1 and A concentration of A 0 to the power minus 1. This means that the half life of the reaction is 0.0259 seconds. For the zero order reaction, half life is decreases with decreasing the concentration. Effect of temperature on reaction rate. First one is temperature dependence. If the temperature is high, the milk attains its boiling point is less time, and if temperature is low, the milk takes more time to attain its boiling point. Normally, the boiling point of milk is not only reaction that gets affected by the temperature. Most of the chemical reactions show the change in the reaction rate with varying temperature. It has been observed that the rate constant for the chemical reaction gets doubled for every 10-degree rise in temperature. Until in 1889, there was no fixed way to physically measure the temperature dependence of the rate of chemical reaction. In 1889, Arrhenius extended the work of J.H. Van 't Hoff and proposed an equation related to temperature and the rate constant for the reaction quantitatively. The proposed equation was named as Arrhenius equation. This is well known equation in chemical kinetics. Arrhenius equation. The Arrhenius equation, which shows the temperature dependence of the rate of the chemical reaction, that equation says K is equal to exponential of EA by RT. K rate constant of the equation reaction, A Arrhenius constant, E activation energy for the reaction in joules per mole, or universal gas constant, T temperature in absolute scale, especially it may be mentioned by kelvins. So, K is equal to EA by RT is well known equation in chemical kinetics, because this is based on the activation energy with the temperature. Activation energy. Activation energy is minimum amount of energy required to activate atom or molecules to a condition in which they can undergo chemical transformation. With a lower activation energy barrier, a greater percentage of reactant molecules are able to have effective collision and the reaction rate increases. Activation energy is denoted by EA. It means that what? Energy of activation. It is usually measured in joules and or kilojoules per mole or kilocalories per mole. The rate of reaction increases with an increase in the temperature, but it was not known how to predict that relation between temperature and reaction rates quantitatively. Arrhenius equation has enabled to overcome this problem. It is an empirical relation that is used to model the variation of rate constant with the temperature, that in turn gives information about the rates of chemical reaction at different temperatures. What are the factors affecting the activation energy? Activation energy depends on two factors mainly. One is nature of reactant, second one is effect of catalyst. So, first one is nature of reactant. In the case of ionic reactant, the value of energy of activation will be low because there is an attraction between reacting species, while in the case of covalent reactant, the value of EA will be high because energy is required to break the older bonds. Second one is effect of catalyst. Effect of catalyst is more major role in chemical kinetics. Positive catalyst provides such a alternative path in which the value of energy of activation will be low. while the negative catalyst provides such an alternative path in which the value of energy of activation will be high. Activation energy does not depend upon the temperature, pressure, volume and concentration. Catalysis. A catalyst is defined as a substance which increase the rate of the reaction without undergoing any change and can be recovered as such as at the completion of reactions. This phenomenon of increase in the rate of reaction with the help of catalyst is known as catalysis. Catalyst means one kind of foreign substance. It should not involve the chemical reaction, it may alter the rate of reaction. Sometimes rate may be increased, sometimes it may be decreased. So, this is a major role in chemical kinetics. Most of the time a catalyst is used to speed up or increase the rate of reaction. In essence, the catalysis encourages the molecule to react and make the whole reaction process easier and efficient. For example, nickel is used in hydrogenation of palm oil into margarine. Second one is the ion. When making ammonia, ion is helpful catalyst. This reaction known as Haber process. It converts nitrogen and hydrogen into ammonia. Ion accelerate the breaking of nitrogen bonds to make it more reactive. Types of catalyst. So, majorly we may consider three types. First one is homogeneous catalysis, second one heterogeneous catalysis and the third one autocatalysis. Homogeneous catalysis. This catalysis in which the catalyst employed in the reaction and the reactant are in the same state of matter, which is called as a homogeneous catalysis. In the same steps as the reactant, homogeneous catalyst work. Usually homogeneous catalyst with the substrate or dissolved in solvent, the effect of H plus ion on the esterification of carboxylic acids, such as the formation of methyl acetate from acetic acid and methanol, is one example of homogeneous catalysis. Example, hydrolysis of an ethyl acetate in the presence of dilute acid. Ethyl acetate is a liquid that contains an ester functional group. It reacts with the water in the presence of dilute sulfuric acid, which is liquid, to give ethyl alcohol and acetic acid. This is a main equation for hydrolysis of an ester. CH3COO-C2H5 is ethyl acetate. Hydrolysis in presence of sulfuric acid. So, catalyst is heat. That means heat is one kind of catalyst. Whenever we are heating, that reaction automatically reaction rate may be increased. Okay. So, finally, we are getting acetic acid as a product, acetic acid as well as ethanol as a product. Your major product is acetic acid. So, in the above reaction, reactant and the catalyst are in the same state of matter, hence it is homogeneous. If you are considering this equation, ethyl acetate is a liquid state, water also liquid state, sulfuric acid liquid state, acetic acid liquid state and ethanol also liquid state, all are having same state. So, this is one kind of homogeneous catalysis reaction. Example 2, oxidation of sulfur dioxide in the lead chamber process. So, 2 moles of sulfur dioxide is reacting with 1 mole of oxygen in presence of NO gives rise to sulfur trioxide. In all the cases, sulfur dioxide gaseous state, oxygen gaseous state, NO gaseous state, our product sulfur trioxide also gaseous state. In all the cases we are getting same state. So, this is also one kind of homogeneous catalysis reaction. Heterogeneous catalysis. In this type of catalysis, that reacting substance in the reaction and catalyst employed in that reactions are not in the same state of manner. Example 1, preparation of ammonia by Haber process. Pure and dry nitrogen and hydrogen gas in 1:3 ratio are passed through a compressor where high pressure of 200 to 300 atmosphere is maintained. In this process, iron oxide is used as a catalyst. It is a solid oxide employed in a process where the reactant are in the gaseous state. The nitrogen gas react with the hydrogen gas to form ammonia as a gas. In the presence of iron oxide solid, thus it is heterogeneous catalyst. In this case, we are considering two different phases, nitrogen gas, hydrogen gas. So, your product also gas, but the catalyst is different, that is solid state. So, this is one kind of heterogeneous catalysis reaction. Hydrogenation of ethane into ethane and the surface of nickel. So, ether and hydrogen molecules are absorbed on the surface of catalyst. Hydrogen occupies most of the activation center and is known as alkylation. So, ethane molecule attack at the double bonds region to form activated complex. Ether react with the active hydrogen to form ethane. This ethane gets dissolved on the surface of the catalyst. So, that catalysis system I have mentioned on the diagram. So, this is hydrogenation of ethane. So, nickel as a catalyst, surface of the nickel, ethane and ethene on the surface of the nickel. So, okay. So, in this case ether and hydrogen molecule are absorbed on the surface of the catalyst. So, in heterogeneous catalyst, the reacting and the catalyst are in different state of the matter. The most important steps in this process are adsorption of reactant molecule activated center, formation of activation complex at the center. This complex decomposes to give product, disruption of product from the surface of the catalyst. Thank you so much.